Assalamu alaikum guys, welcome back with the new lecture. Today we are going to discuss numerical differentiation, how to approximate derivatives basically. So that if you recall from calculus, the formula, which is very well known formula, the derivative of the function at any point x naught is given by this, right? We take the point, any point x naught. So we want to find the derivative here of any function. This is your function f of x. So what we do is we take the increment x naught plus h, right, and find the difference between these 2 points. The difference between these two values, which is this one, and divided by this is h. The difference between these two values is h. So we divide two differences in x and differences in f, and take the limit as h goes to 0. So as h goes to 0, this point moves to this point, right? So I get the slope exactly here, which is f prime. So if I do not take this limit, if I don't take this limit, right, then this, which is the difference quotient on the right hand side, may not be equal to f prime x naught, right? But if we take h very small, we are not taking the limit, but we are just saying that if h is very small, then this difference quotient on the right hand side will approximate f prime x naught. Okay, so this is basically the difference quotient. So we can use this difference quotient to approximate the derivatives, right? And you know that whenever we approximate the derivatives, we are interested in the error, right? So the error in this formula is this. So you can approximate f prime by this difference quotient, but it will give you this much error, minus h by 2 f double prime at xi, right? So I need the second derivative, bound on the second derivative. So if we take the small values of h, the difference quotient, which is this one, right, can be used to approximate f prime x naught with an error bounded by mh by 2. What is mh by 2? This is the error, right? So if I take the absolute error, if I take the mod here on both sides, what will happen? H divided by 2 and the mod of f prime at xi. So what we do is we replace this value by the upper bound of this function, where the maximum value of second derivative, this gives you the maximum bound. So this m is basically the bound on the second derivative. Okay, so this is known as your difference formula. We now, this h can be anything. H can be positive or h can be negative. So if h is positive, we call it forward difference formula, and if h is negative, we call it backward difference formula. Because the thing is, if you go up here, if h is positive, if I take h to be positive, it means I am going on the right side, right? From this point I am going to the right side, so it's a forward difference. But if I take h to be negative, I will go to back. If h is negative, I will go to the left side, so that is the backward difference. So it depends on h, whether h is positive or not. If h is positive, it's forward difference; negative, backward difference. Let's look at the example. Fx is given log of x and point is given 1.8, right? And there are three different h's, so I will get three different approximations. Okay, so first of all, my forward difference formula is, because h is positive, so my f prime at 1.8 is approximately this, right? That it is f of x naught plus h minus f of x naught divided by h. But now this h is different. So if I take h 0.1, I will get a separate answer. For example, if I take h 0.1, then this formula gives me f prime f of 1.8 plus 0.1, which is 1.9, minus f of 1.8 divided by 0.1. So now if you calculate the values of log, so basically this is natural log of 1.9 minus natural log of 1.8 divided by 0.1. So you can find the answer from here using the calculator. So if there will be answer here. So they calculated this, you see, which at 0.1 I got log of 1.9 minus log of 1.8. This is the answer. But he also said find the bound in each case as well. And determine the bounds for the approximation errors. We know that the maximum bound is h by 2 m, right? So h is 0.1, no problem. So that is 0.1 by 2. But what is m here, right? This is the question. What is m? M is the bound on the second derivative. So if you find out the second derivative, let's say, what is the first derivative of the function, which is 1 over x. The second derivative of x is 1 over minus 1 over x square, right? Now you see what is the maximum value of the bound. It is my interval is from 1.8 to 1.8 plus 1, which is 1.9, because h is 0.1, right? So I have x naught and x naught plus h. This is my interval. So between these 2 points, you see x is in the denominator. So what will be the maximum value of this function? The maximum value of this function f double prime of x, the maximum value has to be less than 1 over 1.8 square, right? Because on the left side it will be the smallest. X square will be the smallest at 1.8. So the whole thing 1 over 1.8 will be the maximum value. Okay, so this is we can take this as m. 1 over 1.8 square will be m. Let's say if x square, it is not 1 over x square, it is x square. Now x square will be maximum at 1.9, not 1.8. But if you take 1 over x square, this will be maximum at the smallest value, not at the biggest value. Reason is it is in the denominator. So if the denominator is small, the whole thing will be the maximum. So I can take this as m. Now just put this m here. I got the bound on the error. Okay, so it's calculated here in this example. So they calculated it. You see, a bound on the error is h by 2 xi square. Xi is 1.8, of course. Xi is any point in the interval. This xi is any point in the interval, but I know that on the left hand point this will be maximum because it is in the denominator. Okay, so I got m 0.1 by 2 h by 2 into m, and m was 1 over 1.8 square. So this is the maximum error in this formula. I got this, the derivative. This is my f prime at 1.8, but this is the maximum error here. Approximation error is this. Okay, similarly I can change the value of h. Now he said find the value of h, which is 0.05. Now my formula will become f of 1.85, because x naught plus h is 1.85 minus 1.8 divided by 0.05. So now if you approximate this, your answer should be this one. You can calculate this, your answer should be this one. Okay, this answer should be this one. Okay, and error in this case is again on the left hand side, but now my interval is not 1.8 1.9. Now my interval is 1.85, but again because the second derivative is equal to 1 over x square, right? 1 over x square, so it has to be less than or equal to 1 over 1.8 square one more time, because the left end point is still the same. So this is what I will call m. This is my m. So but now why m is the same but error is not the same? Reason is h is changed. Now my h is not 1.5. You see, h is not 0.1, it is 0.05. So this error is basically 0.05 divided by 2, and m is same, 1 over 1.8 square. Okay, this is my m. So if you approximate, this is the answer. So that's how you can calculate derivatives. But this is the derivative when we use only 2 points. You see here, I made this picture at the top. This is my x naught and this is my x. So this is the slope. This is the slope of the secant line basically, you see. But my tangent line is this. This is the tangent line, right? And this is the secant line. But as we go closer and closer to x naught, means if I take h smaller and smaller, what will happen? This point will go closer here and my secant line will basically approximate. You see, the secant line is going closer and closer to the tangent line. So this thing gives you exactly the slope of the tangent line when h goes to 0. But we are not taking the limit. We are only making h smaller and smaller. So if h is very, very small, then this will approximate f prime x naught. Got it? We can use more points to approximate derivative as well, not just 2 points. So these are the 3 points formula. Okay, the 3 points formulas here are here. So basically here what we are doing is we are taking 3 points instead of 2. We are taking h naught plus h, and we introduce another point h naught plus 2h. Okay, so there are if I use all these 3 points, I can also approximate the derivative at x naught. The derivative at x naught can be approximated using these 3 formula. I need to approximate f prime here at x naught, but I am not just using 2 points now. I'm using x naught plus h, x naught plus 2h. Then this is the formula. I'm not going into the details, but this is the formula which you can use. F of x naught plus h, x naught plus 2h. So see, the function is being used at 3 different points. That's why we call it 3-point formula. And end point formula, why end point? Because x naught is at the end. You see, x naught up to this point. So x naught is your end point of your interval. Your interval is x naught plus 2h. Right, this whole thing is your interval now. So x naught is the end point. That's why we call it end point formula. And this is the maximum error in this formula. See, error is changed. Over there, the error was h by 2. Here it is h square by 3. So it's a better formula. You see, the bigger the power of h is, the better the formula. Right? Because when h is small, h square is even smaller. Okay, so h square is better. So this is your second order approximation basically upon h. Anyway, so we can use the midpoint as well. Midpoint formula. What do we mean by midpoint formula? Midpoint means your h is in the midpoint. Your x naught is in the midpoint. We are using 3 points, but 1 point is taken on the left and 1 point is taken on the right. So this point is x naught minus h. This point is x naught plus h. So instead of taking both points on the right and x naught becomes the end point, here x naught is in the middle. You see, it's the midpoint. X naught is in the midpoint of your interval. So we call it midpoint formula. And here, when you compute the derivative at this point x naught, it does not use x naught. It only uses x naught minus h and x naught plus h. You see, x naught minus h, x naught plus h. But this is still a 3-point formula because in the construction of this formula, we used all 3 points. And this is your bound on the error. H square. This is also of order h square. This was also order h square. 2-point formula was of order h, not h square. Okay, but we need the third derivative here, f cube. It's the third derivative, right? So that these are the corresponding errors. So let's see an example. This is the graphical interpretation of 3-point formula, which is a 3-point midpoint formula. Right? This is 3-point midpoint formula. X naught is in the middle. Okay. So you see the slope of the secant line and the slope of the tangent line, they are very close to each other. Okay. So we hope that they will give a good approximation. Here in this question, there is a 5-point formula as well, but I am not considering that 5-point formula. That's why I cancelled it. Okay. So we are only using the 3-point formula. Values for fx, the function values are given in this table. Okay. He said use all the applicable 3-point formulas. Now he did not say which 3-point formula. Now you see, we want to approximate this as 2.0. So 2.0 is here. We want to approximate our derivative here. It means I can use the endpoint formula. You see, if I take this as x naught, this as x naught plus h, and this as x naught plus 2h, with h is equal to 0.1. You see, 2.0, 2.1, 2.2. So I can use forward formula, means 3-point endpoint formula. I can use 3-point endpoint formula with h negative as well. You see, this is h minus 2h, this is x naught minus h. I can use with h negative, means if I use the same formula with h negative 0.1, I can use these 3 points. So this is the second formula, this is the first one, right? I can also use this as a middle point. I can use this as the middle point. I can take h is equal to 0.1 and use this midpoint formula with 0.1. So see, with 0.1 I will get 1.9, 2.0, 2.1. I can use another midpoint formula, which is if I use just 1.8, 2.0 and 2.2. If I use first one, middle one and the last one, you see, this again uses 3 points. 2 is in the middle, but here h is 0.2, not 0.1. If I use h 0.1, I will use 1.9, 2.0, 2.1. But with h 0.2, I will use 1.8, 2.0 and 2.2. So there are 4 formulas in total. Okay. Endpoint formulas with h 0.1 and h minus 0.1, 2 formulas. Then midpoint formula with h 0.1 and midpoint formula with h 0.2. So there are 4 different 3-point formulas I can use here. So using the endpoint formula with h 0.1, which was the first one I told, this one, second one here, number 2. This is for number 2. I'm using 2.0, 2.1, 2.2. You see, 2.0, 2.1, 2.2. So I'll get the answer, right? Similarly, if I use my negative 1, if I use h is equal to negative 1, I will use this formula. So this one is number 1. You see, h is equal to minus 0.1. If I do that, minus 0.1 will give me 2.1, 1.9, 2.1, 1.9 and 1.8. He did not give the details, but this is the answer you will get. Similarly, you can find the midpoint formula, which is number 3 I wrote over there. This is number 3. Number 1 is this one. This is number 3, right? Midpoint formula x naught plus h, which with h is equal to 0.1. So you see, x naught plus h, x naught is 2.0, right? So 2.0 plus h is 2.1, 2.0 minus h is 1.9. So this is x naught plus h, x naught minus h. So this is the midpoint formula. If I use this one, this should be my derivative. Okay, all the derivatives are very close to each other. You see, 22.03, 22.05, 22.22. Right? Similarly with h 0.2, which is the formula 4 which I wrote, with h is equal to 0.2, you will get 22.41. With h 0.2, what formula I will get? Basically, it will be 1 over 0.4, because this is 1 over 2h, right? The formula is 1 over 2h, you see. The formula is 1 over 2h. So 1 over 2h means 1 over 2 into 0.2. So 2h will become 0.4. Right, 0.4. So 1 over 0.4 and f of 2.2 x naught plus h minus f of 1.8, because it is x naught minus h. And this is what exactly I wrote in the table. You see here in the table, when I take h naught is equal to 0.2, then the points will be used x naught minus h and x naught plus h. So exactly these 2 points came here. Now if you calculate these values which are given in the table and approximate, you should get this answer. Okay, from here. So these are your 3 points formulas. I'm not going to 5-point formula. That can be used similarly, but that's enough. Second derivative midpoint formula. If I want to approximate the second derivative, you know the second derivative is the concavity, right? It gives you the concavity like this. In this whole part, second derivative is negative, right? And if we have this type of shape, the second derivative is positive. So second derivative gives you the concavity, not the slope. But how we can find that? We have a midpoint formula which uses the 3 points. Let's say if I am trying to approximate it here, I need x naught minus h, x naught plus h, 3 points. Okay, so this gives you the 3-point formula for the second derivative, x naught minus h, x naught plus h, and it uses x naught as well, but x naught comes with minus 2, remember. Okay, so this is your second derivative can be approximated by this formula. This is for the second derivative, and this is your error, bound on the error, minus h square. So again, error is of order h square, you see, order h square. So, but it uses the fourth derivative of the function. So let's see an example here. He said in the same example, previous example, use this formula to approximate f double prime at 2.0. So if I use this formula, my f double prime at 2.0 should be approximately 1 over h square. Now what is your h? Now because it uses 3 points, x naught minus h, and x naught plus h. So you can use either 0.1 or 0.2. So if you use h is equal to 0.1, it will be 0.1 square f of 1.9 minus 2 f of 2.0 and plus f of 2.1, right? So this will be my answer because it uses point. If you want to use h is equal to 0.2, this is with h is equal to 0.1. Okay, because my table also has values 1.8 and 2.2 as well. So if I use here, if I use value 1.8, then this automatically becomes 2.2, right? Because this is with h is equal to 0.2. But outside it will be 1 over 0.2 square, right? And f of 1.8 minus f of 2.0, because midpoint is the same, plus f of 2.2. So this is your formula. These are two separate answers, but here this is with h is equal to 0.1, this is with h is equal to 0.2. So these are calculated. Of course, the values are given in the table. You just have to pick the values. So you see, with h is equal to 0.1, with h is equal to 0.2. Now just pick the values from the table. These values are given in the table. You don't have to calculate. So 29.59 and 29.70. Of course, if h is smaller, you see, with h is equal to 0.1, this should be better to the original derivative. Okay, so this is this was the numerical differentiation. Okay, this was all about numerical differentiation. In the book, there is another formula given, which is a 5-point formula for the first derivative. If you want to just see it, you can see it, but I am not including it in the syllabus. So numerical integration, numerical differentiation, we have simple formula, which is straightforward from calculus, which is of course 2-point formula. X naught and x naught plus h, or x naught minus h, forward difference, backward difference, both can be used. Then if we want to use 3 points, then there are two separate formulas for the 3-point formula. One is end point formula, means when x naught is at the end. Okay, and midpoint formula means when x naught is in the midpoint. The center point is your x naught, where you are looking the derivative, calculating the derivative. Okay, so that's it for numerical differentiation. So I will be back with numerical integration in our next video.